last class we derived the real and imaginary component of the stator and rotor voltage equation with respect to a general rotating dq reference phase, and the general rotating with a speed of omega rho. If you see here, d rho by dt is equal to omega rho. So, with respect to this is omega rho is measured with respect to our stationary alpha beta axis. Now, based on this equation, let us formulate our dynamic dq equivalent circuit. So, d rho by dt is omega rho. This is the general rotating reference frame speed. So, again we will rewrite this one and formulate our dynamic equivalent circuit model. So, let us write down stator, Vs B is equal to Rs ISD plus LSS d by dt ISD minus LSS omega rho into ISQ plus m into d by dt IRD. IRD means the rotor d-axis current minus m omega rho IRQ. This is the stator VSD. Then stator VSQ. VSQ is equal to, see, if you see here the stator, the d by dt ISD, this will take care of the magnitude variation and this will take care of the speed variations, correct? So, VSQ, but the due to the speed variation, it will go to that term will go to the V in the q axis. So, VSQ is equal to Rs ISQ plus LSS d by dt ISQ plus LSS omega rho ISD plus m into d by dt IRQ plus m omega rho IRD. This is the stator. Now, let us take the rotor. So, here dq axis applied voltage is 0. So, that is equal to RR IRD plus LRR d by dt IRD minus LRR omega rho minus omega r. See, the voltage term due to the rotation at the rotor is the relative speed. Rotor is already rotating with omega r and our rotating reference frame is omega rho. So, relative speed is omega rho by omega r. But if you see the stator, it is omega rho because stator is stationary. So, the rotating voltage, the voltage due to the rotation omega rho is depending on the speed of our reference frame axis. Omega rho minus omega r into IRQ plus m into d by dt ISD minus m into omega rho minus omega r into ISQ. This is the rotor D axis. Now let us take the rotor Q axis. This is equal to 0 is equal to RR IRQ plus LRR d by dt IRQ plus LRR into omega rho minus omega r into IRD plus m into d by dt ISQ plus m into omega rho minus omega r into ISD. Okay. Now let us, based on this dynamic equation D and Q, see what we did. First we defined the voltage and starter voltage space vector for the starter as well as the rotor with respect to alpha beta reference frame axis. Then we transferred the whole voltage term to the general rotating reference frame axis dq. The speed is the position of the general rotating reference frame axis with respect to alpha beta axis is rho at any instant, and d rho by the speed of rotation is omega rho. Okay. Then we separate into real and imaginary component, the D and Q component. Now we got the dynamic equation under all conditions. That means when the amplitude as well as the speed or the frequency varies. Let us take the first starter equation. So there is a VSD voltage we are applying. So this is VSD. Here maybe we will use a different color so it will be clear. Applied voltage. So here there is a drop RS ISD. This is RS. ISD is this one. ISD is flowing like this. Then LSS d by dt ISD. So LSS is equal to, if you see, LSS is equal to M plus leakage inductance LS. Okay. So let us draw the leakage inductance here. This is LS, and there is LSS into ISD. So this ISD is going to the mutual inductance also, then only you can say LSS. So mutual inductance here. This is M. LSS ISD. Now if you see here, these are voltage term due to the rotation. That means this one and this one, that is this one and this one. This we can write down, if you see here, LSS plus omega rho ISQ plus IRQ. So this is due to the Q axis. So the rotational voltage due to the current in one axis will appear at the other axis, other orthogonal axis. So before coming to that one, let us take the rotor term also. Rotor term RR IRD. So we have RR here, RR IRD here also, plus LRR d by dt of IRD. LRR is equal to M plus LR, leakage inductance. So we have the leakage inductance here. Okay. So this also comes here. So through the mutual inductance term here, both ISD and IRD is flowing. So, IRD is here. Okay. Now, what is this LSS omega sigma ISQ plus IRQ? This is, we can say, the flux psi SQ. So, we will come to that one now later, so that we will follow. So, there is a rotational voltage term appearing at the starter due to ISQ and IRQ. That means current flowing through the Q axis equivalent circuit, these two, and this is minus. That shows, see, we have taken current entering as positive. Okay. So, this is minus means current comes ISD, it comes like this. So, we can take it this time as negative positive. So, current entering is taken as positive. So, the term is like this. So, this is a function of omega rho multiplied by LSS ISQ plus M into IRQ, Okay. What is this one? Will come to that one. Similarly, rotor circuit, the D axis, LRR, that is this term. ISQ. Here also it is negative. So, with respect to IRD, if you say negative means, we will put it like this and go. So, this is negative, this is positive, because IRD is going like this. IRD is entering the negative side. So, that convention we followed. So, this will be equal to, this also a rotational voltage term, that is also equal to omega rho minus omega r into LRR IRQ plus M into ISQ. Okay. This is the D axis. Similarly, we can write the Q axis. Q axis, let us start with VSQ, applied voltage VSQ. And this is the ISQ. So, we have the RS term here, RS ISQ, again the leakage LS and the mutual M here. Similarly, for the rotor side also, you have leakage inductance LR and the resistance term RR. Oh, this is RR, rotor resistance. Here also the voltage term. So, the voltage terms polarity, if you see here, for the Q axis, this is the one, this is one, and the next one is due to the rotational. So, IRQ, M into IRQ, IRQ is coming this way, ISQ is coming there. ISQ, it goes through LS plus M, that is why LSS. Now, that voltage term we will put it like this here due to rotation. Starter side it is omega rho into LSS ISD LSS ISD plus MIRD plus M into IRD. This is the term, and polarity, this is positive, that means current is entering the positive terminal, notation like this. Here also, rotor side also IRQ, there is omega sigma minus omega r, omega rho minus omega r, that is these two terms. LRR IRD plus M into ISD. Okay, this is the term. So if you see here, LSS ISQ, LSS ISQ is this one, LS plus M, and ISQ is flowing here, then M into IRQ, IRQ is here. So there is a current IRQ flowing here and ISQ flowing here. So if you see here, what is this one? This is called, that is ISQ plus IRQ, that is called psi SQ, flux psi SQ, phi SQ. Similarly, this one is equal to phi psi RQ. This is the flux coupling this mutual and this LR. Similar way, we can say this one is phi RD flux. This is phi SD, the flux which is coupling this LX and M due to this LS and M and the current flowing through it. This is phi SD. So if you see here, what is this equation? Omega rho, this equation is equal to omega rho into phi SQ, this one. And what is this one? Omega rho minus omega r into LRR IRQ. LRR IRQ means plus M ISQ. LRR IRQ is this one, total flux, plus M into ISQ. So this is psi R, psi RQ. This is equal to into phi RQ. So due to the flux and the rotation, there is a in the Q axis there is a voltage term in the D axis, starter and the rotor. Similarly, here, what is this term? This term will be if you see here, this is omega rho into LSS ISD, that is this one, plus M into IRD, that is this is phi SD, omega rho phi SD. And similarly, we can find out this term will be omega rho minus omega r into phi RD. So our dynamic equivalent circuit is ready. This can also, we can represent in this in a matrix form. See, using this equation. Let us say, let's go to the next page now. See, let us see, we have, let us take omega rho is equal to omega s. If you put it our dynamic equivalent circuit will be with respect to a synchronous reference frame. Omega rho is equal to 0, then it will be stationary reference frame. Stationary, that means omega rho is equal to 0 means dq will be aligned with alpha beta, that is stationary alpha beta, the reference frame. So let us write down in matrix form the equation. This will be, we have 4 stator voltages, that is VDS, VQS and the rotor 0 is equal to, we have 4 currents also. So, this is a 4 by 4 matrix. One, 2, 3, 4. Here also 2, 3, 4. This is our IDS, IQS, IDR, IQR. So, VDS, the first term, RS plus d by dt of LSS. D by dt we will say P LSS. P is an operator. P is equal to d by dt. Then this one will be minus omega s LSS. Term will be here. Here will be m into P. P is d by dt. Then minus m omega s. Okay? That is the stator D voltages. Then stator Q voltages are LSS omega s, then RS plus P LSS. LS, this P means d by dt of IQS. Okay? Then m into omega s. See, that is, we are taking everything into synchronous reference frame, that is the subscript s, synchronous reference omega s. Then m into P, P is the d by dt. Again here m into P. Rotor, the relative speed is omega s minus omega, minus of omega s minus omega subscript r into m. Then rotor resistance and the self inductance drop, RR plus P into LRR. Then minus omega s minus omega r into LRR. So, rotor D axis voltage time is over. Now, rotor Q axis, this is omega s minus omega r into m, that m into P, omega s minus omega r LRR. Then RR plus P LRR. P is the d by dt, as an operator. See, we have the, we got the machine dynamic voltages in matrix form. So, here, okay, we can either use equivalent circuit or this one. If you see here, what is the torque produced? the torque produced is power divided by the frequency of operation. So, if you see here in this equation, the torque is power divided by the speed. So, power means voltage into current. So, the torque produced and that voltage which is responsible for the torque is due to the rotational voltage. Okay? Because of the rotation we get the torque. So, all the rotational voltages multiplied by current, that is the power which is responsible for the torque production. So, if you see here, which are the ones here in equation? One time is here, one time is here, then here, here, then here from the rotor side this one, these are the terms. So, let us take out the power. P is equal to, we can write minus omega s into LSS. Okay. So, this into IQS. This is the voltage, okay, at the d axis. Then there is another voltage term minus m omega s into IQR, that is minus omega s m into IQR. So, this is the voltage term appearing at D, and the current at the D is IDS. So, we have to multiply this one with IDS to get the power at the D axis. Then the Q axis stator, again this will be equal to omega s LSS IDS, that is this voltage term, correct. There is another voltage term here, plus omega s m, and the current is IDR. This is the voltage term. So, multiplied by IQS is the power at the stator. Now, let us take the rotor. Rotor DR, that is minus of omega s minus omega r into m into IQS, again there minus by omega, so that we can club together, plus this term LRR into IQR. The whole thing is multiplied by, now this current is in the D axis by IDR. Okay. Then again the Q axis plus omega s minus omega r into m into IDS, that is this current m into IDS, then omega s minus omega r plus LRR into IDR multiplied by IQR. This is the total power. So, but we know that, see, this IQR and IDR, rotor current, is very difficult to measure. So, we have to replace IQR, IDR in terms of rotor flux, but rotor flux information we want. But from the previous equation, we know that psi RD is equal to m into ISD plus LRR IRD. So from this one, what is IRD? We can find out what is IRD. We can find out IRD here in terms of ISD and the rotor flux. Similar way, psi RQ is equal to M into IS Q plus LRR IRD. So from here, IRD we can select based on this one, psi RD and psi RQ, because we want the rotor flux information. Final power equation will be M by LRR into psi RD ISQ minus psi RQ ISD. Okay. This way final equation will come. But if you see here, this has to be and multiplied by omega s. Omega s will come. Now for the torque, you have to divide by the mechanical speed. Omega mechanical is equal to omega s divided by P by 2. So T is equal to P by omega mechanical. P is the number of poles, so P by 2 will be equal to P by 2 M by LRR into psi RD ISQ minus psi RQ ISD. It will get this form, torque. So when we divide by the omega mechanical, P is the number of poles. Number of poles. Now let us see, we have transferred everything from the 3-phase to 2-phase. So any transformation, the power balance should be met. That means in any reference frame, the power balance should be equal. The power should be equal in any reference frame. The power should be the same. That is, power balance should be met. The power should be the same. Let us say whether alpha beta transformation and find it to dq, whether the power balance is met. Now for a 3-phase power, power based on single phase equivalent quantity is equal to 3 into for RBC system 3 into V phase into I phase. Okay. Suppose we are that same voltage waveform we are sending it to a, let us say we are going to a resistive load to make it simple. So this transformation, the voltage and current transformation is it is not independent of the load. So let us take a resistive load. So 3 phase into I phase, 3 times for 3-phase power. Now in our transformation, we have found out that I alpha is equal to 3 by 2 IA, A phase, or V alpha is equal to 3 by 2 VA, V phase. Okay, V phase. Here also we will say I phase value. Now alpha beta means 2-phase power. So 2-phase power will be the 2-phase power is equal to 2 into V alpha into I alpha. Same resistive load, we are trying to find out the power in the alpha beta reference frame. This will be equal to 2 into 3 by 2 into 3 by 2, 3 by 2 into 3 by 2 into V phase into I phase equal to 9/2 V phase into I phase. So, the power balance for the 3 phase it is this one, for the 2 phase it is this one. So, to meet the, see with the transformation we have taken, we have not taken into consideration the power balance. We simply assume the number of turns are same for the alpha beta and transfer the voltage and current. Now, to make the power balance in our to make it 3 V phase into I phase, in the 2 phase quantity we have to multiply by 2/3. So, correspondingly torque also we have to multiply it by 2/3. So, here in our transformation this is the final 2/3 P/2 is the number of M/LRR, this is the torque developed in the system in terms of rotor flux and the starter currents. See, we got the transformation equation, dynamic condition under DQ reference frame. Now, what we want, this is the alpha beta and this is our D and Q. DQ is rotating synchronous reference frame, we made it. Now, we want to, suppose our psi r, rotor flux is here, somewhere here. This is our phi r flux space phasor, that is phi r is equal to phi r d plus phi r q plus j phi r q. So, which is phi r d? Phi r, you project this one to this one, this is phi r d and this will be equal to phi r q, this is our orthogonal component. Now, for field oriented control, or vector control, for high dynamic applications, performance similar to a separately excited DC machine. DC machine, what we want? The phi r flux space phasor should be aligned always along the d axis. So, what is meant by that one? See, if you see here, see, we will just rewrite this one here. That means, in our new reference frame, alpha beta, this is our D, perpendicular to that one we have the Q, and our psi r, this is synchronous voltage, psi r should be always along this one. So, what is meant by this one? Phi r along this one means in the new reference frame, and if it is 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 here, this is our IS, this is our new ISD and this is the ISQ. In this phi r, the phi RQ is equal to 0. That means the new reference frame phi r magnitude is equal to phi r d. So, we have to meet this condition. That means we should know the instantaneous position of the psi r, and we have to align the psi r along our rotating synchronous rotating dq axis. Now, in this case, let us see what is our equivalent circuit. So, let us go to our new reference frame and find out what happens in the new reference frame. So, we will draw this one here, our alpha beta. Alpha, this is beta. Now, our d axis, this is our d axis, this is our q axis, and psi r also along this one. Phi r. Now, we have to resolve the current space vector. That current space vector is here. This is our IS. Will be splitting along D as well as Q. This is ISD and this is ISQ. So, ISD component will be proportional to the responsible for the flux phi r. Now, in the new one also here in the new reference frame phi r d, phi r q is equal to 0. So, let us go to our torque equation, original torque equation. Torque equation when psi r q is equal to 0 is 2 by 3 P by 2 M by L r r. Finally, equation will be phi r d into ISQ, because phi r q is equal to 0. So, in this equation, by keeping ISD constant, phi r d is kept constant. So, flux magnitude is kept constant. So, this shows torque will be proportional to ISQ. So, by varying the orthogonal component, perpendicular ISQ component, the decoupled torque control is possible. Torque control is possible. Okay. Now, we said psi QR is equal to 0. Let us go back to our, now how the equivalent circuit will work. Let us go to our equivalent circuit. Let us go to the next page. So, our equivalent circuit is like this. Let us take the Q axis, VQS. This is minus plus omega s psi ds, then leakage inductance RR, this is our IQR, this is our IQS, this is omega S minus omega R into psi dr. Now psi QR is equal to 0. In the field oriented reference frame, psi QR is equal to 0. Which is psi QR? Psi QR is the one due to these two fluxes. This is M, LR, LS. What shows? That means d by dt of psi QR also 0. So the voltage coming across the resistance RR is equal to the rotational voltage, this one. So if you write down the voltage loop equation here, let omega S minus omega R into phi dr plus RR IQR is equal to 0. That means rotor circuit equation, if you take it, your d by dt psi r is equal to 0. So that means this rotational voltage will be should be dropped across the resistance RR. So from this one IQR. Now psi QR is equal to 0. That is, what is psi QR? M into IQS plus LRR IQR is equal to 0. From here, from this one, minus IQR is equal to M by LRR into IQS. So we got IQR in terms of IQS. What is omega S minus omega R? Omega S minus omega R is the slip. So omega S minus omega R into phi dr is equal to, from this equation, that is from this equation, is equal, substituting IQS, that means M by LRR IQS RR. What is this one? This is slip. This one is the omega slip. So finally what we get? Omega slip into phi dr is equal to M by LRR into IQS into RR. Okay. So psi dr is constant. Psi dr is constant. So that means omega slip is proportional to IQS, the orthogonal component. Here omega slip into phi dr is equal to M by LRR into IQS into RR. That shows phi dr keeping constant by keeping the ISD component. Phi dr is keeping constant, then omega slip is also proportional to IQS. Omega slip is proportional to IQS. Previously we have shown under field oriented control or field oriented equivalent circuit, the torque is proportional to IQS. That means the torque is, slip is proportional to the torque. Slip is proportional to the torque by keeping phi d are constant. Then by varying the orthogonal component, we can vary the slip, and in turn we can control the torque. So, we will continue this analysis, field theory control, in the next class.